group working in collaboration with open force fields. I did most of this work while I was a PhD student in Julian Michel's group. So what is the problem and why should you care about it? Well, initial bias is a problem in free energy calculations. So when I was a PhD student, I spent a lot of time running absolute binding free energy calculations. Super expensive, meaning the data are precious. However, my expensive data were often contaminated by initial bias. That is the issue which is illustrated in this plot here. In my case, quantity X would be something like gradient, shown with respect to the sampling time. And the issue is I have unrepresentative initial configurations, which are giving me this initial transient and initial bias. To give you a concrete example of a sampling issue which could be causing this bias, imagine I'm running an absolute binding free energy calculation of this complex. Imagine at some intermediate value of lambda, the ligand should be partially decoupled, and it's extremely favorable for this water to be in the binding site. Because of how I've started it, the water is not in the binding site, and maybe it takes a while on the timescale of the simulation for water to move into the binding site. This could be accompanied by a substantial change in my free energy estimate before it starts to fluctuate around something which is more representative of the long-time average. It doesn't really matter what the sampling problem is, but this creates an issue for analyzing the data. So how do I process it? I want to estimate the answer that I get from running a simulation for an infinite amount of sampling time. The problem is if I just naively average all of the data or plug it into mbar, I create a substantial amount of bias. So what's shown on the right is the error with respect to the infinite sampling time result. The overall is in red. We have this bias component in purple, and we have the random component in blue. You can see we get substantial bias from the unrepresentative starting configurations. The typical approach to deal with this is truncation of the data. So you throw away some data from the start of the simulation, and this reduces the bias substantially. The problem, of course, is if you keep doing this, you're going to increase the random component of the error because you just don't have much data. So you, of course, want to pick the truncation point, which biases these two competing factors and gives you the optimal truncation point. Of course, this is an impossible problem to solve completely because we do not know the infinite sampling time mean. We're trying to calculate it, and we cannot calculate this decomposition on the right. The question then becomes, how do we make the most effective use of this really expensive free energy data? How do we do it in an automated way? Because a fixed truncation point is unlikely to be optimal across a diverse range of systems with diverse initial transient behavior. And how can we automate this truncation point selection? So firstly, what methods do we already have to do this? So there's methods from Yang based on reverse cumulative averaging, where the idea effectively is to take the end of your data, analyze it back the way, take a putative equilibrated region and extend it back through the simulation, checking for deviations from normality. When you detect those deviations, you say, this is the border region that distinguishes my equilibrated and equilibrating regions. One disadvantage there is you are assuming normality. Another really nice method from Guidara is based on maximizing the effective sample size. So what we have here is the estimated standard error, which is a function of your truncation time, divided by the estimated standard deviation, also a function of truncation time. And we're picking the truncation point to minimize this. This is really nice, widely available through PyMBar. An issue I'd argue, though, is it's not being thoroughly assessed on test cases which are representative of challenging use cases. And also, this is actually really closely related to a heuristic which is popular in the operations research community. So this is White's marginal standard error rule, or MSER. You can see this looks extremely similar to the maximum effective sample size metric. In fact, these perform pretty similarly in practice, and the main difference is how we calculate the standard error typically. So because these two methods are a little bit simpler, they don't assume normality, we're going to look at these. Because they're actually very similar, we're going to look purely at the marginal standard error rule. We're going to look at applying this on data and using different methods to calculate the standard error. So to reiterate, the issue is how do we select the truncation point in a robust way? And the answer we've selected to this is to try using the marginal standard error rule. To reiterate again, we do not know the infinite sampling time mean. We cannot calculate this error decomposition. So what we do instead is we calculate the standard error using the sample mean, which of course we do know. We get a curve which looks like this, which we minimize by truncating the data. And we hope that this is a reasonable proxy for the true underlying curve of the error. The question then becomes, how should we calculate the standard error, which is not trivial? The remainder of the presentation is going to be as follows. We're going to look at a few different ways for calculating the standard error in the context of the marginal standard error rule. We're going to then look at testing it on a wide range of synthetic data. And I'll come back to why we're doing that later. And we're going to assess the performance by the minimum RMSE over these data sets. So firstly, why is it hard to calculate the standard error? So you're, of course, extremely familiar with the basic formula for calculating squared standard error, the variance to the mean. You can put n-1 to correct the bias if you want. For simplicity, we have this. So we're just, of course, taking the average of the deviations from our sample mean. But the problem is, of course, that when we run molecular simulations, we almost always get correlated data. So the problem here is each sample point has some dependence on the previous one. We're getting less information with each new sample point on the position of the mean. And if we use these formulae to estimate the standard error, we're going to get a massive underestimation. So what we can do instead is we can estimate some of these autocovariance terms to estimate the variance. So these autocovariance terms are a function of t, which is the lag time, and n, which is the number of samples. These, again, are just an average of some deviations. If we have lag time 0, this is just the same as the uncorrelated case, where we're just taking the square of these deviations. But as we increase the lag time, we're spacing out these two deviation terms. So with a lag time of 4, you can see there's 4 data points separating these two deviation terms. And we keep increasing these lag times as these deviations become less and less correlated. So if we plot how these terms look as a function of the lag time, you can see they start up pretty high and decay down towards 0. And you might think we could estimate the standard error by simply adding up all of these terms. The issue is that this is a really bad idea because they do not converge to 0 as the time goes to infinity. Instead, you end up dominating your sum with error. So we need to come up with smarter ways of calculating this sum. So one naive approach you could take to this is simply ignore the autocorrelation. So this is what's done in the original marginal standard error paper. Another popular approach, which I'm going to call Kadari's method, is simply summing up this until we get the first negative value, which we assume is unphysical. We also tried adding in a weighting function, this window function here, and what this does is simply scales down the importance of the autocovariance terms from 1 to 0 over some interval, for instance, size 5. And we also used window size of root n, where n is the number of samples, because of its popularity in Markov chain Monte Carlo for calculating confidence intervals. Finally, we also looked at another class of methods called Gayer's initial sequence methods, which I'm not going to go into in detail. They're effectively a slightly more complicated way of deciding where to truncate your series and enforcing some conditions. I'm just going to group these in with Kadari's method for the purposes of this talk. So then how do we test these methods? Ideally, we'd have infinite compute. We'd run an enormous number of simulations representative of challenging use cases. But the issue of that is it's extremely expensive to do that. We can't get enough data in order to get good statistics when we're testing our methods. So we've opted for a compromise. And what we've done is we've taken real data. We've used this to generate synthetic data, which we hope is representative enough to generate some useful insight in how these methods are performing. And this allows us to generate as much free data effectively as we want for testing our methods. So how have we done this? Well, this is based on fairly long absolute binding for energy calculations. So we have here 5 complexes that I've run 30 nanosecond per lambda window absolute binding for energy calculations for. This encompasses a diverse range of systems with diverse initial transient behavior and error. What we've done is we've taken the true for energy estimates shown in black here. This is 5 replicates, and we're just using TI for simplicity here. And this is not a cumulative average. This is pretty much instantaneous. We fit with 3 components. So we have a bi-exponential fit for the transient. The last 20 nanoseconds of the data is approximately stationary. There's not really an overall trend. So we fit to that a Gaussian. We found that this was well modeled by Gaussian noise. But crucially, we've also fit the autocovariance function to this portion of the data. So that we do this for all 5 systems. Then we can generate as much synthetic data as we'd like for each real system. So for each real system, we do 1,000 synthetic runs. What we do is we generate uncorrelated Gaussian noise. We reintroduce the desired autocovariance structure based on the fit and add back in the bi-exponential. And now we have many, many data sets, synthetic data, that we can use to assess the performance of these methods. So how do these methods perform then? So firstly, let's look at this qualitatively. And the nice thing about generating your data synthetically is that you know exactly the underlying properties of your data. So just taking one system here, we've taken just the first 8 nanoseconds to be more representative of what you might actually run. I'm showing you the decomposition of the overall error in red as a function of the random component and also the systematic component in purple. And you can see that the optimal fixed time truncation point is given by the minimum of this curve at just over 4 nanoseconds for this system. What we can then do is we can apply the marginal standard error rule using all of these different methods for calculating the standard error. And we can look at the distributions of discard times that we're getting with a histogram shown in the middle. So we can distinguish some trends. So from top to bottom, we have methods which don't really account for autocorrelation at all, moving on to methods which more thoroughly account for this autocorrelation. The methods which do not account for autocorrelation have a tendency to produce really high bias because we truncate really early, for example here. As we move on to these methods which more thoroughly account for autocorrelation, we can end up with more variance because we get wider distributions of these discard times. To get a feel for what's going on, we can look at a single example of a synthetic run. So that's what's shown up here. We have the free energy estimate as a function of simulation time. I've shifted the final result to 0 for simplicity, and this is showing you the results that we get with the uncorrelated method. On the bottom, we have the variance of the mean estimate, and we're minimizing this to decide on our truncation point. Or equivalently, we're maximizing 1 over this to decide on our truncation point. And you can see we get a pretty smooth curve here. The maximum is too early, resulting in early truncation. And you can see this is a case across the data set. So this is pretty insensitive to the bias. If we then move to a method which more thoroughly accounts for autocorrelation, here using the window size with root n, we start to get a slightly later peak. We end up truncating a bit later, more close to the optimal truncation point here. So this is, in general, we found a reasonable compromise. And the issue is, as you go to some of these methods which are more thoroughly accounting for autocorrelation, we end up with very noisy curves here of 1 over the standard error or variance estimates. We have these peaks here, which come from differences in where you're truncating the sum of autocovariance terms. And you can see they're really quite prone to effectively gaming this metric. They pick the last little portion of the data, minimizing variation about the sample mean. And this effectively games the metric and can lead to truncating late. Although I should comment, in all cases, we've excluded the last 10% of the data because it just gets too noisy. So these can be highly variable and can be prone to late truncation. So let's try and be a little bit more quantitative now. This is just the plot I showed you in the previous slide. And this is the system, the real system that we use to generate this data. In addition to looking at the discard times, we can look at how this actually translates into the error. So the minimum possible error is shown by this black dotted line here. You can see that if we truncate too early, this translates into pretty high RMSE over the data set. But as we go to these methods which are truncating later, we do get closer to the optimal truncation RMSE. However, this does vary a lot depending on the system. So if we look at data modeled on a different real system, which has more pronounced initial transient and higher error, we have a much earlier optimal truncation time here. If we plot the discard times, we can see something which is pretty worrying, which is we have a bimodal distribution of discard times for these methods, which are more thoroughly accounting for autocorrelation. So this really is a bit of a problem because it does translate into higher RMSE across your data set here. So if we look at our full set of synthetic data runs, we can distinguish 2 cases. So firstly, the 3 systems in the middle. We can see that the methods which are not fully accounting for autocorrelation are truncating early, introducing substantial error compared to what we could be getting with the optimal truncation point. However, if we look at the T4 lysozyme and phosphodiesterase 2A systems here, we can see that these methods which are more thoroughly accounting for autocorrelation quite often end up truncating too late or have bimodal distributions, which are introducing more error. At least on this data, we found that using the window size method with size root n hasn't done much worse than the optimal methods in all cases, at least on this data. We've also done a few other experiments. So firstly, we wanted to see what happens if we run basically a control. What if you don't have an initial transient? Therefore, the optimal truncation time is 0 and you shouldn't be throwing away any data. So this data just looks like this, just fluctuation about 0 effectively. Well, in a case where there's reasonably high error, but we still have a lot of effective samples, actually some of these methods truncate far too much data. Some of the methods which more thoroughly account for autocorrelation can sometimes discard up to over half of your data, even though we have no initial transient. So we should be aware of this limitation when applying these methods. Another thing is, well, it'd be really nice if we could use these methods to decide how long should I run my simulation for, rather than just saying, I have this data, how much of it should I use? A heuristic which is often used in the operations research literature for deciding this is looking at the truncation point. If I truncate over 50% of the data, we say I've not run enough, and we keep running. So where we experimented with this was just feeding in only a very small amount of the synthetic data right from the start, so just first 0.2 nanoseconds there. We end up with extremely biased data with a large initial transient or a steep transient. And we find for some systems, in general, it does truncate most of the time over half, but this really doesn't look reliable. You've got wide distributions. But for most of the systems, in fact, they completely failed to discard over half of the simulation time. And in general, we really wouldn't recommend these methods for deciding have I run for long enough rather than just a post-processing step. We also wanted a bit of reassurance that if we use different data, we'd come to similar conclusions. So we tried, for instance, running with noisier data for which we got similar results. We tried mimicking the effect of, for instance, saving the data less frequently by subsampling. And this does reduce the autocorrelation and somewhat reduces the differences between methods. But in general, we get similar results there. So to conclude, the marginal standard error rule is a simple and appealing truncation heuristic method, which is similar to maximizing the effective sample size. Within the marginal standard error, failure to account for autocorrelation produces large bias. You tend to truncate too early a lot of the time. If we went to the methods here which more thoroughly accounted for autocorrelation, this did reduce the bias, but you can end up truncating too late. They effectively game the metric, which can be an issue. And at least on this data, we found the window method with size root n seemed to strike a reasonable compromise between the bias and the variance for this data. If you're interested in more details, please check out the paper. I would like to finish with a few suggestions for practically applying these. So firstly, don't expect too much. You saw the wide distributions you're getting of the discard times. Secondly, I think it's actually likely to be a better way to do it by feeding in data from multiple replica runs. The code does this, but we have not yet tested it. Be wary of applying these methods to decide how much to run for rather than just a post-processing step. And be aware that we've optimized for a slightly different problem than estimating the error. So I think you could look at that with similar methods, with similar synthetic data, but we're not optimizing for estimating the error accurately here. Finally, if anyone's interested in this, this is implemented in a package which is available through Conda Forge. It'd be fantastic if anyone could try this, let us know how it's performing. We've got an interface which is really similar to the PyMBar detect equilibration function. Thanks to Molsey and Simon Boothright for Cookie Cutter. And finally, I'd like to say thank you very much to Julie Michelle, to Danny Cole, to the Michelle Group, to Graham Robb at AstraZeneca, everyone who funded this, so EPSRC, AstraZeneca. Thanks for the conference organizers, and thank you to you all for your attention. Happy to take any questions.
Thanks, Finlay, for a very interesting talk.
Thanks.
We have time for one question. Anyone?